Hello students, welcome to my new video. Today we are going to discuss about one more topic from class 12, that is Wheatstone bridge. Now before seeing Wheatstone bridge, I request all of you, those who have not seen my video, the previous video about KIRCHHOFF'S law, okay, I request you to please go and watch those videos carefully, because to understand the concept of Wheatstone bridge, you need to understand KIRCHHOFF'S law first. Okay. Now, students, I have seen in many books the place where the Wheatstone bridge is given. I have seen they are directly giving a diagram of a balanced Wheatstone bridge and what a balanced Wheatstone bridge looks like. But before that, you have to first understand the basic concept of a Wheatstone bridge and how to apply KIRCHHOFF'S law in Wheatstone bridge. Okay, so let's see. Now, Wheatstone bridge was first, it's basically a network of resistance, a bridge, it looks like a bridge network of resistance which was devised by Sir Charles Wheatstone. Okay, it was devised by Sir Charles Wheatstone. So first you have to understand what is a Wheatstone bridge. So Wheatstone bridge is a combination of resistance. It is basically an arrangement of resistance in a very peculiar way. Okay, so it basically looks like this. Over here we have one resistance. Now the diagram that I am drawing, this is the basic diagram of a Wheatstone bridge. Then we will be discussing about balanced and unbalanced Wheatstone bridge. Students, please don't first jump into unbalanced Wheatstone bridge. First you have to understand the principle of a Wheatstone bridge and how to apply KIRCHHOFF'S law in Wheatstone bridge. Okay. So basically this Wheatstone bridge is a network of 4 to 5 resistances. So these are the two resistance. Over here we have one resistance. Over here we have one more resistance. Okay, so these are the 4 resistances. Suppose P, Q, R, S. Okay, these are terminals A, B. Over here I have connected one cell and one key. Suppose it is EMF. Internal resistance I am considering it to be 0 for now. Okay. From here to here I have connected one more resistance. This is one more resistance. Okay, suppose T, resistance T. Okay, now this particular arrangement, okay, as you can see in the board, this particular arrangement is known as a Wheatstone bridge. Okay, there are 5 resistances. Okay, there are 1, 2, 3, 4, 5. There are 5 total resistances. Okay, now first you have to see how current flows through it. The basic concept of Wheatstone bridge you have to understand and see how current flows in this particular device, in this particular Wheatstone bridge. Now as you can see from the diagram, okay, if I ask you to find out the equivalent resistance, you will not be able to find out, because over here you see, if you see the diagram, you will not understand which one is in series, which one is in parallel. These two are not in series, of course, because here is one more branch. Okay, then again this one and this one, you cannot say that they are in parallel because over here there is one more branch. Okay, so you cannot do it in the conventional way. You cannot solve it in the conventional way if you want to find out the equivalent resistance or if you want to find out the current in each branch. So we have to take the help of KIRCHHOFF'S law. Okay, we have to take the help of KIRCHHOFF'S law to solve this one. Okay, suppose from here current I is flowing. Students, please, before seeing this video, please go and watch my previous videos on KIRCHHOFF'S law. Okay, basically KIRCHHOFF'S second law we require over here. Suppose current I is flowing through this branch. So suppose I is flowing through this branch. Now see, over here there are 2 branches. So suppose I1 and I2. I1 and I2. So I1 is flowing through here, okay? It flows up to this point. Suppose these 2 points are C and D. Okay. Now after I1 flows up to this point, again you see there are 2 more branches. Okay. Again you see there are 2 more branches. Suppose through this branch I3 flows. Then through this branch how much will flow? I1 minus I3 will flow through this branch. Okay. I2 is flowing from here. Over here there is I1 minus I3. Okay. In this particular branch, you see this current and this current will meet over here. This current and this current will meet over here, and in this branch we will get I1 minus I3 plus I2 in this branch. Okay, so this current will flow through here, and through here I3 is coming. Fine. This current and this current, they are going to meet at this particular place. So here we will get I1 minus I3 plus I2 plus I3. So I3 will be cancelled. We will get I1 plus I2. And we know I1 plus I2 is basically equals to I, because initially I was only divided into two currents, I1 and I2. So I1 and I2 is equals to I. So through this branch, current I will be flowing. Okay. So this is the division of current. This is how current is going to flow through this branch. Fine. Okay. Now students, some of you have a confusion. Okay, some of you have a confusion. I have seen that they ask me, sir, why current is flowing from C to D? Okay, why this current is branching and why this current is not branching? You see, what I am saying is that the circuit could have been like this also. This is one resistance. This is one resistance. This is the width, suppose. Okay, so from here I1, I2. Now what I have said is that, what I have shown here is that this I1 is divided into two branches. Okay, but suppose, can this be the case? Listen very carefully what I am saying. Can this be the case? Suppose I2 is coming from here and this is the resistance. Okay, and suppose I2 is dividing into two branches. Suppose this is I3, this is I2 minus I3, and I1 is flowing through here. So, and they are meeting over here. Okay, so over here I have shown current is flowing from C to D. So that is the question. Can current also flow from D to C? So this is point C, this is point D. So here I have shown current is flowing from C to D. Can current also flow from D to C? That means suppose this current I am dividing into two branches and they are meeting over here. Okay, this I1 and I2 minus I3, they are meeting over here. Yes, that is also possible. Okay, but that is not clearly given in any of the books I have seen. But that is also possible. You see, students, in which direction current is going to flow, that depends upon the potential difference. Current always flows from a higher potential to a lower potential. Over here, I have considered that point C is at a higher potential, point D is at a lower potential. Okay, but if point D is at a higher potential, point C is at a lower potential, then of course current is going to flow in this direction. Understood? Now, which one will be at higher potential? We don't know, because you see, it depends upon the resistances. These four resistances, or all these resistances. Okay, it depends upon the resistances, because we know whenever current crosses a resistance, that time there is a potential difference. Okay, unless we know the value of the resistances and unless we know how much potential is dropping, we will not be able to say which terminal is at a higher potential. Everything depends upon the potential, the resistances. Okay, the potential and the resistance. If C is at higher potential than D, then current is going to flow from C to D. If D is at higher potential, then current is flowing from D to C. Okay, so I hope your doubt is clear. Fine. Let's continue with this one. But you see, whether current will flow from C to D or whether current will flow from D to C, it doesn't matter. It will not affect whatever we are trying to do over here. Okay. Now basically what we will do now, first we will choose the loops over here. You see, this is loop 1, this is loop 2. Okay, and we are going to apply KIRCHHOFF'S law over here. Okay. So suppose loop 1. Okay, loop 1. Okay. Now in loop 1, you see, suppose I want to go in this direction. I told you the next thing you have to do is choose your direction. Okay, you have to choose your direction. How to apply KIRCHHOFF'S second law. So here I am applying KVL or KIRCHHOFF'S voltage law. Okay, I am applying KIRCHHOFF'S voltage law. Okay. So from here I am going. You see, I am going in the direction of current. The potential difference over here is I1 into D. Since I am going in the direction of current, so you know, you will take it with negative sign. Okay, down the direction of current. Okay. Again over here there is one more resistance and the potential difference is T into I1 minus I3. So T into I1 minus I3. Okay, now see again we are going down the direction of current, so again I will take minus sign. Fine. Okay. So now again over here there is one more potential difference, that is R into I2, but over here we are going up the current. Up the current means plus sign. So plus I2 into R, that is equals to 0. So this is our equation for loop number 1. If you want, you can just simplify this one, I1T minus I1T plus I3T plus I2R equals to 0. This is your equation 1. Okay. Now let's take loop 2. Again applying KVL, Kirchhoff's voltage law. Okay. So this is your loop 2. Suppose I want to go in this direction. I want to go in this direction. Fine. I want to go in this direction. Okay. So let us see. Suppose we will start from here. We are going to start from here. Okay. So in this branch, current is I3 and resistance is Q. So I3 into Q. You see over here we are going up the current. Up the current means positive. So plus. Okay. Now again we will be coming over here. Over here the potential difference is T into I1 minus I3. Okay, T into I1 minus I3. But over here we are going down the current. Down the current means minus. So minus T into I1 minus I3. Okay. Again we are going over here. Okay. So here you see here how much current is flowing. I1 minus I3 plus I2 into S, that much is the potential difference, and we are going down the current. Okay, down the current means minus. So minus S into I1 minus I3 plus I2. So there are no more potential differences, so this one is equal to 0. If you want to simplify, I3Q minus I1T plus I3T minus I1S plus I3S minus I2S, that is equals to 0. Okay, so this is your equation for loop number 2. Now students, you see in the previous video I told you how many loops you have to take depends on how many currents you have to find. Over here you see there is I1, there is I2 and there is I3. There are 3 currents. So at least you require 3 equations. But over here we are getting only 2 loops. Okay, over here we are getting only 2 loops. So one more loop you have to take. Either you can take this whole loop, entire one, or you can take this loop. Okay, you see here also there is one loop. Here also there is one loop. Okay, so this loop also you can take. Suppose this loop I am taking loop 3 and I will be going in this direction. Okay, that means this. So I will be going in this direction, clockwise direction. Okay. So loop 3. Again applying KVL. Okay. So we are going to start from here. Okay, fine. We are going to start from here. So I2 into R, down the current. So down the current means minus I2 into R. Okay. From here. Okay. Over here again S into this I1 minus I3 plus I2. Again we are going down, so that means minus S into I1 minus I3 plus I2. Okay. Over here you see we are crossing this EMF, this cell, and we are crossing the negative terminal first. So I told you if you are crossing the negative terminal first, the EMF will be with plus sign. Okay. So plus E, that is equals to 0. Okay, plus C, that much is equal to 0. Okay. Now, if you want to simplify this one, I2R minus I1S plus I3S minus I2S plus E equals to 0. So this is your equation 3. Okay, so these are your 3 equations. Now, if you know the value of R, okay, if you know the value of R means if you know the value of all the resistances and if you know the value of EMF, then by solving these 3 equations, okay, by solving these 3 equations, we will get the value of I1, I2 and I3. Okay, So you will get the value of I1, I2 and I3. Right? So this was all about Wheatstone bridge. Right? Okay. Now see students, in the books you will find balanced and unbalanced Wheatstone bridge. But before that you have to first understand the concept of Wheatstone bridge and what does a Wheatstone bridge work. Okay. So this is the basic diagram of a Wheatstone bridge, and first you have to understand this one. Don't just dive into balanced and unbalanced Wheatstone bridge. This is how a Wheatstone bridge works. This is how current is going to flow through the Wheatstone bridge, and this particular network is known as a Wheatstone bridge. Right? Now what is an unbalanced Wheatstone bridge? Okay. Now we say that an unbalanced Wheatstone bridge is a Wheatstone bridge over where through this bridge, you see this particular thing, it basically looks like a bridge. Okay, this is known as the bridge. Okay, this wire, this is our main concern, because you see if this wire were absent, if this wire is absent, then very easily we can do these two are in series, these two are in series, and then we can solve in parallel, right? But our main problem is this bridge. This connecting bridge is our main problem. So if current is flowing through this bridge, okay, here I'm writing, if current flows through CD, if current is flowing through this bridge, then we say that this is an unbalanced Wheatstone bridge. Okay, this is an unbalanced Wheatstone bridge. Unbalanced Wheatstone bridge. So then we are going to say this is an unbalanced Wheatstone bridge if current is going to flow through that bridge, either from C to D or from D to C. Okay. In most of the cases, current flows through the bridge, but the questions that you get in the exam, most of them are balanced. They always, most of the times they give with balanced Wheatstone bridge. But students who are only focusing with balanced Wheatstone bridge, and if you don't know how to solve, in case if you are given an unbalanced Wheatstone bridge, then this is the how we can solve by applying KVL. Okay, fine. Now remember students, the thing that I told you, at the potential at which C and D will be, the potential at which C and D will be, that basically depends upon the resistances, how much resistance we will take and how much potential drop will be there. Okay, it will depend upon the resistance. Remember this one. Okay, so now if you understand this one, very easily we can understand the concept of a balanced Wheatstone bridge. Okay, now let's see what is a balanced Wheatstone bridge. So this one I am learning. So balanced Wheatstone bridge. Balanced Wheatstone bridge. Now see students, suppose, okay, so before saying balanced Wheatstone bridge, let me first rub the currents over here. Okay, this currents and this one. Okay. Suppose we choose the value of these four resistances in such a way, remember this one, suppose P, Q, R, S, okay, over here there is T also, this one let it be whatever it is, okay. These four resistances, we choose the value of resistances in such a way so that terminal C and D, they are in the same potential. They are in the same potential. Okay, I told you if you have an unbalanced Wheatstone bridge, then either C can be in higher potential or D can also be in higher potential. But and it also depends on the value of resistance. Okay, which terminal is at a higher potential. But if I choose the value of these four resistances in such a way, there is a particular formula, that formula we will get at last. Okay, if we choose it in such a way that this potential difference, okay, this potential difference VC and this potential difference VD, okay, they become equal, then what will happen? So this potential and this potential, they become equal, then what will happen? Okay, students, you see, current always flows from higher potential to lower potential. If current finds that there is no potential difference and two terminals are at the same potential, if current finds that, then current is no longer going to flow through that particular branch. Okay, so if this potential and this potential they become same, then current is not going to flow through this branch. Okay, current is not going to flow through this branch. So through this branch you will get current zero current. Remember, our basic concern was this connecting bridge. This was our problem. Okay, if this bridge is not there, then very easily we can solve the problem. Okay, so if this potential they become equal, then no current is going to flow through this branch. In some of the books you will see over here they have connected a galvanometer. Instead of this resistance they have connected a galvanometer, and the so it's very easy to understand. The galvanometer will give you zero deflection. If no current is flowing, then the galvanometer will show you zero deflection. Okay, also along with the resistance you can connect a galvanometer also, no problem. Okay, I have not shown a galvanometer, same thing, just basically simply I am telling you that no current is going to flow through this branch. Okay, now see, if no current flows through this branch, okay, we can eliminate this one. Then see, P and Q will come in series. Okay, you can write this one, P and Q. P and Q will be coming in series. R and S will be coming in series. Why, you see? Because the current which will be flowing through here, I1 is flowing through here, it will not be divided into this branch. So over here also I1 will be flowing. I2 is flowing through this branch. Over here it will not be divided. So here also I2 will be flowing. So these two branches have the same current. So these two are in series. These two are in series. So R and S are in series. R and S are in series. Fine. And then these two are in parallel. Then these two branches they will be parallel. Okay. Now the question is how to find out the value of PQRS, or what is the relation. When will this happen? When will this particular case of balanced Wheatstone bridge happen? At what particular condition? Okay, so we have a condition. So to solve that, again we have to use Kirchhoff's law. So suppose loop 1 I have taken, loop 2 I have taken. Remember, now this branch we will not be taking because over here no current is there. Okay, so first suppose loop 1. Loop 1 I am applying KVL, Kirchhoff's voltage law. Okay. So I1 into P, down the current. I hope all of you can understand now. I1 into P. Okay. Here we have no current, no current, no current. Over here I2 into R, up the current. So plus. So plus I2 into R. Okay. That is equals to 0. According to KVL, the sum of the potential differences across any closed loop is always equal to 0. This is your equation 1. Okay. Next we take loop 2. Loop 2, again we will apply KVL. Okay, so suppose we will be starting from this point. So from this point we will be starting. So I1 into Q, so that will be minus because down the current. Over here I2 into S, up the current. So plus I2 into S, that is equal to 0. No more potential differences over here. Now you see, the case where we had unbalanced Wheatstone bridge, over there we had 3 currents. That was the main problem. Over there we had 3 currents because current was also flowing through this branch. Fine. So over there we need 3 equations. But over here you see, since no current is flowing through this branch, so our 2 equations is enough. Okay, by using 2 equations we can solve this one. Okay. Now see, if you just simplify this one, from here what we will get? We will get I1P equals to I2 into R. From here we will get I1Q equals to I2 into S. Okay. If you divide these 2 equations, we will get I1P by I1Q equals to I2R by I2S. Okay. So these 2 will be cancelled. P by Q will be equals to R by S. Fine. This is the condition. This is the condition for a balanced Wheatstone bridge. Please write it down. So So this is the condition for a balanced Wheatstone bridge. Okay. So if this resistance divided by this resistance equals to this resistance divided by this resistance, in that situation no current is going to flow through this particular branch. Okay, and if no current is flowing through this particular branch, easily you can use this method to solve the equivalent resistance. Fine. So first, students, whenever you will be getting this circuit, now this example, suppose if I say that this is 10 ohm, okay, this is 100 ohm, suppose. So P by Q will be how much? 1 by 10. This is suppose 100 ohm, this is suppose 1000 ohm, okay, so this is also 1 by 10. So in this particular condition, no current is going to flow through this branch. Okay, that one only we have derived, that whenever we have done it basically the back process. Okay, so if no current flows through this branch, then what is the relation between PQ and S? This is the relation between PQ and S. So first, students, once you get the circuit, okay, once you get the circuit of a Wheatstone bridge, you will have to solve this one. Your first task is to check whether this is a balanced or unbalanced Wheatstone bridge, because in the question it will not be said to you in most of the questions. Okay, so first you have to check. Okay, just take these 4 resistances and check whether it is a balanced or an unbalanced Wheatstone bridge. If it is a balanced Wheatstone bridge, then you are lucky. If it is a balanced Wheatstone bridge, then easily you can solve. You can take these 2 in series, these 2 in series like this, and then in parallel, and easily you can solve, or you can find out the current. So, or you can use KIRCHHOFF'S law to find out the current. But if you get an unbalanced Wheatstone bridge, don't just expect that always you will get a balanced Wheatstone bridge. If you get an unbalanced Wheatstone bridge, in that case you have to solve by the previous method which I have shown you. You have to take current through this branch. Okay, you have to take current through this branch, and then you have to solve using KIRCHHOFF'S law. Fine. So that was all about Wheatstone bridge. That was the main basic concept of Wheatstone bridge and what is a balanced and unbalanced. You see, balanced and unbalanced Wheatstone bridge comes at last. First you have to understand what is a Wheatstone bridge and how to solve that one. Fine. Okay. So that was all about today's video. If you like the video, please like and subscribe. If you have any questions, please let me know in the comment section below. Thank you.